So now we are ready to go on to those equations of cosmic dynamics. There are actually three of them, and they are the Friedmann equation, the fluid equation, and the acceleration equation. And this is going to be another thing we've done a lot in this course, which is where I outline the steps you have to go through and then say if you want to actually go through these steps, it gets very complicated and there's lots you have to do. I do apologise for that because in a sense it's an inevitability of this course. What I have done in the PDF for this week, if you want to go and look at the end of it, is I have actually gone through those steps. Hopefully that will be something of a relief for those of you who hate the phrase "it can be shown." But on the other hand, hopefully when you look at the amount of work you actually have to do to get there, you'll see why it is necessary to say it can be shown, rather than spending the entirety of an hour and a half lecture slot slogging through Christoffel symbols and so forth. And so we can look in general terms at the things we have to do. So to get these equations, firstly, of course, you have to go from the interval to the metric. So identify all the different bits. So for example, you can say that GRR is just equal to minus r squared over 1 minus kr squared, etc. Having got the metric, then you need all the connection coefficients. And this is a relatively straightforward metric, but it still has many non-zero connection coefficients. So you need to get all of those. You can use the metric and those coefficients to get to the Ricci tensor. And then you can use that Ricci tensor in combination then with the actual field equations to get differential equations that give you the scale factor, the fluid density, etc. And remember, you've got the field equations which give you T alpha beta for a perfect fluid. And so what you have is you have the Friedmann equation. And that comes from the spatial part of the metric. RR theta theta phi phi. And it says the following: A dot over A squared. Remember, that's the Hubble parameter, h squared, equals 8 pi g over 3 c squared e on epsilon minus k c squared over a squared. And we have the acceleration equation, which comes from the TT part of the metric. And it is A double dot over A equals minus 4 pi g over 3 c squared e plus 3p. And then we have the fluid equation, which you can get in a couple of ways. Essentially what you can do is you can do just the time derivative of the Friedmann equation and substitute in for a double dot from the acceleration equation. Or you can go, if you want to, like that, because you're worried about the fluid, you can also go from the covariant derivative of the stress energy tensor. And what that tells you is that E dot plus 3 A dot over A E plus P equals 0. And so these equations, which do conveniently fit on a single view graph here, I shall put them in boxes. Interesting. They are your equations of cosmic dynamics. If you solve them, you know how the energy density and the scale factor will evolve with cosmic time, and you can therefore derive how the size, i.e. the scale factor of the universe, changes with cosmic time. And they are exactly the same as the Friedmann fluid and acceleration equations that exist in Newtonian cosmology, with really the crucial thing that you have an explanation for why you have a curvature sitting up here. It's not obvious in the first instance why that curvature actually exists. And it's not also really obvious why you have pressure either in that Newtonian model. So those are the sort of the crucial changes. And something you can notice, I've already said, the universe that we live in has k equals 0. And if the universe that we live in has k equals 0, then there is only one allowable density at any given cosmic epoch or Hubble parameter or scale factor, if you like, that you can have. And so we call that the critical density. Three c squared h squared over 8 pi g. This is not a constant. Okay, as the universe gets bigger, things like photons and radiation dilute away, the density of the universe goes down, but it is still the critical density. And so it's all compensated for by what this Hubble parameter, this h squared, is actually doing. And just for sort of convenience, we often express this as a parameter omega, which is equal to E over E crit. So for example, earlier when I said that matter was 27%, or 4% plus 23% for baryonic and dark matter of the density of the universe, what I meant was that omega matter is equal to omega baryons plus omega dark matter equals 0.04 plus 0.23 equals 0.27. Or I could say that omega r is 10 to the minus 4, or that omega lambda, or perhaps more formally, dark energy, is equal to 0.73. So it's quite common for me to express things in this fractional form because the actual physical value of the density evolves dramatically with time. The contributions also evolve dramatically with time, but it's easier if things are listed in this sort of simple fractional way. And very importantly, if the universe has a critical density at any time, it has the critical density at every time. So if k equals 0, E equals E crit, always even though E crit evolves with time. So in other words, if the critical density now is 1, the critical density in the past was higher, but the universe still had it. And then there's one other thing that we should note here, which is, as well as having a critical density, we can also look at this role of the cosmological constant. And the cosmological constant is a very specific form of dark energy. And it exists for a reason. Because in 1917, Einstein decided that general relativity was wrong. And he decided to write R alpha beta minus a half R G alpha beta plus lambda G alpha beta is equal to some constant, the normal constant, times T alpha beta. And here, lambda is cosmological constant. It's a fluid of constant density and negative pressure. And just to put that into context, if I look at the acceleration equation, minus 4 pi g over 3 c squared e plus 3p, that doesn't appear to allow me to have zero acceleration. Because the pressure, the energy density has to be positive by definition, and you'd think the pressure has to be positive. So for A double dot equals 0, E plus 3p equals 0, and I have to have a negative pressure. And you think of a negative pressure as a tension, something that pulls it apart. And therefore, Einstein put this in because he realised when you have matter, you have radiation, all of these are positive energy sources, positive energy density. They act to create curvature, which causes the universe to slow down. And therefore, in order to have a steady state universe, he believed that you had to put something in which counteracted that and held the universe in check. He later referred to this as his biggest blunder. He really realised, when Hubble realised the universe was expanding, he scrapped this out, and for the best part of a century, the field equations stood without lambda in. They were only added back in about 20 years ago when observations of both the cosmic microwave background and a distant supernova started suggesting that in fact there was a negative pressure which was causing acceleration of the universe. So it didn't actually balance this to zero. It was actually causing universal acceleration.